Hi everyone. In the last session, we have discussed about Ohm's law, and in today's session, we are going to discuss on Kirchhoff's law. Objective: at the end of this video, you can be able to A. Connect the components in series and parallel. B. Prove Kirchhoff's voltage law. C. Prove Kirchhoff's current law. Part 1. Introduction to series circuit. First, let's discuss on series connection. A series circuit or connection is the one where all components are connected end to end, forming a single path or line like a human chain. In the same way, in a series circuit, all the components are connected, one end to the other end of another component, and so on. Here, resistors R1, R2, R3, and R4 are connected one after another in series to form a single path. Example 1. Three people, A, B, and C, are walking on a single path to reach the destination. Since there is a single path to reach the destination, all three people have to travel on the same path. Likewise, in a series electrical circuit, current flow remains the same due to a single path. Example 2. Here, water pipe is connected between the tanks in series. Hence, water flow rate will be the same in the pipe. In series electrical circuit, current flow will always be same due to a single path. In a series circuit, if any of the components fails, then the entire circuit fails due to no path for current. Introduction to parallel circuit. Let us discuss on parallel circuit or connections. Parallel circuits or connections are ones where components are connected with multiple paths or ways. Here, resistors R1, R2, R3, and R4 are arranged in such a way that the top ends are connected together and their bottom ends are connected together. Let us discuss with an example. Here, three people, A, B, and C, have three individual ways to reach the same destination. Person A may reach the destination quicker than B due to a shorter route or less traffic, and person B may reach it quicker than C due to a shorter distance. Likewise, in parallel circuits, current flow differs according to the resistance in the path. Let's discuss another example. Here, water flows from the main tank to three different tanks through pipes. At a point, you could see a junction where water flow is separated. Let us assume at the junction, water flowing inward may be 10 liters, it may be separated by 5 liters to tank A, 3 liters to tank B, and 2 liters to tank C, depending upon the size of the water pipe. When you add the amount of water flows to tanks A, B, and C, you will get 10 liters, which makes a total of 10 liters of water. So finally, at a junction, inward water is equal to outward water. In the same way, the sum of the current flowing towards the junction is equal to the current flowing outward. In parallel circuit, current is always divided on each branch depending on the resistor value. In a parallel circuit, if any of the component fails, then particular branch alone will not get the current flow, but the rest of the circuit will get current flow, hence the rest of the bulbs are on. All the domestic wiring and street lighting use parallel connections. Introduction to Kirchhoff's law. Let us discuss series and parallel circuits using the laws. Kirchhoff's law is used to demonstrate series and parallel circuits. Kirchhoff is a German scientist who provides two laws, the first and second laws. Kirchhoff's first law shows the behavior of voltage and current in series circuits. Hera's second law shows the behavior of voltage and current in parallel circuits. Kirchhoff's current law. First, let us see Kirchhoff's first law, which is also known as current law. Kirchhoff's current law states that total current entering or flowing towards the junction is equal to total current leaving the junction in an electrical circuit. In other words, at any node of a circuit, the sum of the currents into the node is equal to the sum of the currents out of the node. The amount of current flowing out of a node equals the amount flowing in at any instant. In other words, an electrical node acts like a junction of water pipes where the amount of water going out equals the amount coming in. Case 1. In case 1, you could see two branch circuits consisting of resistors R1 and R2 at the same values are connected in parallel, and the total current flowing through the network is 10 amperes. Here, both resistors have the same values, so at the junction J1, current I1 and I2 are equally divided. According to Kirchhoff's current law, at junctions J1 and J2, total current entering the junction is equal to current leaving the junction. Case 2. In case 2, two resistors R1 and R2 have different values of 6 and 4 ohms, so current flow through each resistor will not be the same. At the same time, you may notice that the current flowing through the higher resistor value is less and the current flowing through the low resistor value is greater. As a result, the current flowing I1 in a 6 ohm resistor will be less and greater in a 4 ohm resistor, given that current is inversely proportional to resistance. But at the junction J1 and J2, the incoming and outgoing currents are same, which satisfies Kirchhoff's current law. Case 3. In case 3, let's have a parallel circuit with the resistors R1, R2, R3 and R4. Assume the total current flowing in the circuit is 10 amps. Here, you can see that in parallel circuits, current flows in all the branches depending on resistor values. More current will flow in the low resistance branch, while less current will flow in the high resistance branch, and all current will return with the same amount of current. Hence, Kirchhoff's current law is satisfied. Task 1. Let's prove the Kirchhoff's current law in practical. Step 1. Here you can see a simple circuit consists of a voltage source or battery and three resistors R1, R2 and R3, which are connected in parallel with each other and to the source. Step 2. All three resistors are connected in parallel to the source, one end to the positive terminal and the other end to the negative terminal, similarly to voltmeter connections. Step 3. The same voltage will exist across the resistors that you set
battery with variable power supply
due to parallel connections. As we discussed already, current I is distributed in all three branches as I1, I2 and I3 in R1, R2 and R3 resistors respectively. Step 4. Now connect a voltmeter in parallel across the variable power supply unit, an ammeter in series with a voltage source, and 3 ammeters in series with three resistors R1, R2 and R3 with appropriate range using wire. Step 5. Ensure the common ammeter range is large enough to carry all three branch currents I1, I2 and I3. Step 6. Set different voltages in the variable power supply unit and check the voltmeter and ammeter readings with a given tabulation. From the tabulation, ammeter reading I is equal to sum of the ammeter readings I1, I2 and I3. Hence, Kirchhoff's current law is verified. Kirchhoff's voltage law. Let's move on to Kirchhoff's second law, which is also called Kirchhoff's voltage law. As Kirchhoff's voltage law describes the behavior of voltage and current in a series circuit, Kirchhoff's voltage law states that the algebraic sum of all the voltages around any closed circuit is equal to 0. Before discussing the law, we need to understand voltage drop. What is a voltage drop? A voltage drop is a decrease in voltage or voltage loss that occurs when current flows through the resistance. You already know that resistance is the property of the conductor that opposes the flow of current, and that current flow is caused by voltage or EMF. If food is wasted, it does not become a loss to the person who is cooking. It becomes a loss to the person who spent the money to buy the food. Likewise, the resistance will affect the voltage or EMF but not the current. The amount of voltage drop can be measured by connecting a voltmeter across or in parallel to the resistor. Case 1. In this case, resistor R1 and R2 with the same value are connected in series with a voltage source. The voltage drops across R1 and R2 are measured using voltmeters V1 and V2 respectively. Because they have the same values, the voltage drop will be the same. The sum of voltage drops V1 and V2 will be equal to the input supply voltage, so the remaining voltage is zero, hence Kirchhoff's voltage law is verified. Case 2. Here, two resistors R1 and R2 are connected in series with a voltage source. The voltage drop across each resistor is measured with two voltmeters V1 and V2 respectively. Since the resistor value R1 is greater than R2, the voltage drop V1 across the resistor R1 will be greater than V2. Ensure of voltage drops V1 and V2 is equal to the input supply voltage to prove Kirchhoff's voltage law. Thank you for watching and have a good day.